All right, it is 12:30, so let's begin. Today, we're going to talk all about the electron transport chain. We started this discussion last week, Thursday, and got into talking about complex 1 here, where we take NADH, and we are giving 2 electrons to Q. Then Q is going to be our electron carrier. And we talked about how in complex 1, we have this whole system where NADH gives us electrons to FNN, and then using these iron sulfur complexes, we transfer electrons all the way to Q. And we just do it one at a time, where we just keep transferring one electron, one electron, one electron, one electron in a safe way, so we don't lose those electrons in the cell where they can cause real damage. So we're going to continue talking about the different complexes. Reminder that next week, Thursday, is test number 2. So this week's material will be on that test. What we talk about next week, Tuesday, will not be. But yeah, just keep that on your calendar. It should be next week, Thursday, if I have my dates right, test number 2. Right, so let's get into it then. Let's continue to talk about oxidative phosphorylation. So, like I said at the very beginning there, we are transferring electrons from NADH, and ultimately we want to bring them to coenzyme Q or CoQ. As coenzyme Q, it's going to bring it to our next complex. When we do this, we are also pumping out hydrogens from the matrix to the intermembrane space. So matrix. So remember the matrix, just as a quick little reminder of what the mitochondria is. We have an outer membrane. We have an inner membrane with all these cristea, so I'm not going to draw that very well. This is a really bad drawing, but it'll get the point across. So you have an outer membrane, inner membrane. Inside the inner membrane is the matrix. And then between the outer and the inner membrane is the inner membrane space. So we're taking hydrogens from the matrix to the inner membrane space. Now, one thing that is interesting about complex 1 when you look at the structure of it is that all the electron movement happens in the arm, while all of the hydrogens movement happens further down the protein. And by the way, I just noticed it said cytoplasm and periplasm here. All the complexes that we talk about, they have been originally studied in bacteria. So bacteria don't have a mitochondria, so they don't have the matrix and inner membrane, but the way they do oxidative phosphorylation is basically the same as we do it. So don't be confused by this periplasm, cytoplasm business. And so the question is, when we look at complex 1, how does a reaction that happens up here affect the rest of the protein so that it can bring in hydrogens? And this is something we talked back in biochemistry 1 for different proteins, especially when in terms of hemoglobin. It's all due to conformational changes. So what happens is that Q gets 2 electrons, and it will stay in the binding site as this negatively charged Q, Q2 minus. When that happens, these blue arrows, what they're showing is they're showing how the protein responds to this negative Q. You have this conformational change. And this conformational change is kind of felt throughout the whole protein. These red arrows are trying to show, how do different amino acid side chains move, right? So the arrows are kind of like hydrophilic amino acids. The red spheres, they are lysine and histidine, and the blue spheres are glutamic acid. So you have these movements between hydrophilic amino acids, and you have this movement between your charged amino acids. And this movement is really what is facilitating the movement of the proton. Because if we just look down here, a proton comes in, binds to glutamic acid, and the way it's going to move between all these different amino acids till it finally reaches the excess chamber is something called proton hopping. And it's proton hopping. We talked about that before in terms of water. Basically, what that means is that proteins don't physically move. And it's better to be shown in water. So if I have H3O plus, and I have another water, what will happen is that H3O molecule will give a hydrogen to this water. And if I have another water right down the chain, instead of giving the same hydrogen, it'll just pop that hydrogen over, so on and so forth. That's called proton hopping, and that makes hydrogens appear that they travel way faster than physically possible. That's also going on here as well. You have some water in complex 1 that is facilitating this proton hopping. But yeah, that is how we have something that happens all the way down here in the protein affect the rest of the protein to allow it to pop out hydrogens. It's through this proton hopping. And this happens, like I say here, roughly 200 times per second. So it's extremely fast. And then what happens for Q? When Q is about to leave, it will pick up 2 other protons and it will leave as QH2. And it will allow QH2 to travel through the lipid bilayer until it comes to complex 3. So that's where QH2 is trying to go to, complex 3. But overall, that is basically how complex 1 works. We talked about on Thursday how electrons are moving, and right here is how the conformational change is happening, how the different protons are going from one side of the membrane to another. So is there any questions about the information presented here? And by the way, for another image of proton hopping, that's what this image is showing over here, how a proton can go from one side of a protein to another. This is not complex 1, by the way. This is in your eye. It's how you see, which is basically what's happening here, but it's the same concept. All right, there's no questions about this. We can move on. As always, if you are typing on a question and I move a little too fast and you're not finished, feel free to continue to type it out and put it and enter it, and I'll answer it when I see it pop up. All right, so this last problem is just a something for you to remind yourself and a good studying tool when it comes to the test. Just go back to these slides, see if you can put in your own words how complex 1 passes electrons from NADH to ubiquitin, and how protons are pumped from complex 1. That's what I'm mainly looking for. If you know this biochemistry, just this level, just tell me, what's happening with the iron sulfur complexes and all of that. But with that, I think that ends the little bit we had to do on Thursday. And so we'll pick up with our new PowerPoint that I put out this morning. So let me pop that up. Tuesday, March 9th. All right. So we're going to continue with our complexes now. And next is complex 2. And one thing to note for the electron transport chain, even though it's named complex 1 and complex 2, you never go from 1 to 2. What you're doing with complex 1 is that you're making QH2. This QH2 goes to complex 3. Same thing for complex 2. You make QH2, and that goes to complex 3. So it's like you start at one of them. You never go 1 to 2 because they do the same thing. You go from 1 to 3 or 2 to 3. So the question is then, why do we have two different complexes that seem to be doing the same thing? And that's because they have different substrates. Complex 1 is getting fed in NADH to make NAD+. And by doing that, they can pump out hydrogens. Complex 2 is using succinate, which we saw in the citric acid cycle. So we're taking electrons from succinate. However, you cannot pump out hydrogens. There's not enough energy going from passing electrons from succinate to coenzyme Q to pump out hydrogens. So the question is, why do we do this? And the reason is because those electrons are still useful for us further down the line, right? That Q, as we're going to see today, can still do a lot of cool biochemistry, can still pump out protons later on in the process. But from complex 2 directly, no, you cannot pump out hydrogens, right? So how does it read in succinate? That's because complex 2, whoops, that was a bad line, but it has succinate dehydrogenase, our friend from the citric acid cycle, contains succinate dehydrogenase. So the citric acid cycle, that reaction happens in complex 2. Again, like we saw in complex 1, the same type of mechanism is used to pass through electrons. First, we have FAD. And again, FAD is used because it can deal in 2 electrons or 1 electron. What I mean by that is succinate will give 2 electrons to FAD, and then FAD will only pass one of those electrons off at a time. Most molecules can't do that. Most molecules can usually only deal with 1 electron at a time or 2 electrons at a time. FAD is one of the rare molecules that can do either 1 or 2. And these iron sulfur complexes, same thing as in complex 1. They're there to safely move these electrons around to keep them within the complex so they don't leave the actual protein. So that's our little chain here to coenzyme Q and to become QH2. You'll notice there's a little heme down here. The last we saw heme was in Biochem 1 when we were talking about how to move oxygen around in the body with hemoglobin. Well, heme is just a catch-all word for that type of molecule. So there's a lot of hemes in your body, not just in hemoglobin. Here, heme acts like a net. So that's shown right here. That heme group, and it's also shown right here. That's what that green thing in the middle is. That's heme. And this is FAD. So they did a pretty good job of color coordinating the image to what the protein actually looks like to our flow chart here. So this heme, is kind of like a safety net, right? If an electron, happens to leave this iron sulfur chain and not go to coenzyme Q, heme is there to like absorb it, soak it up, so it doesn't go into the cell and ruin your DNA or ruin protein. So it's just a safety mechanism there. It's like a safety net. So any electron that happens to not go to coenzyme Q will again just be absorbed by heme in complex 2. And that's basically what complex 2 is doing. Again, succinate electrons, go to coenzyme Q, ship the coenzyme Q off to go to complex 3. So any questions about the information presented here for complex 2? All right. That moves us on to complex 3, also known as coenzyme Q, cytochrome C, oxidoreductase, or cytochrome BC1, or just complex 3, much easier to say. Now, all of the coenzyme Qs that we have made in complex 1 and complex 2, they are harvested in complex 3, where we're going to take the electrons and move them to cytochrome C. So just a little note about our electron carriers. Coenzyme Q, that is traveling in the membrane, while cytochrome C, that travels into the inner membrane space. So it's not in the lipids. You can even see in the picture right here, cytochrome C is already poking out into the intermembrane space. And so what cytochrome C will do when it gets to the electrons is it will leave this protein, travel in the inner membrane space, and go to complex 4. To move the electrons around, we have things that we have seen in the other 2 complexes with these iron sulfur clusters. They, again, help us to move electrons around safely. We also have the cytochromes, which are going to be our catchers, and we have hemes. These hemes, again, are very important for moving electrons. So unlike complex 2, where the heme was a safety net, here in complex 3, which we're going to see on the next slide, they are very important for showing how this molecule works, or they're very important in actually moving electrons around for us. This is a very big protein, 75 angstroms just poking into the matrix. Angstroms with a little circle. I'm sure 75 angstroms, not sure what that means to you. A lot of proteins, a lot of folded proteins aren't 75 angstroms long themselves. So it's just a massive, massive complex. So and 40 angstroms thick. So the width across is 40 angstroms. So it's a very, very long protein that is doing, that is complex 3. So let's actually look at how complex 3 works in something called the Q cycle. Okay. So what we're looking at here is a schematic version of complex 3. And this whole process, this is complex 3. This whole process is getting electrons off of Q and to get them to cytochrome C. And it's done in 2 steps. So the top of this picture is like step 1 or phase 1. The bottom picture is step 2 or phase 2. So let's go through the Q cycle. So either from complex 1 or complex 2, QH2 will come and bind complex 3. And there are 2 binding sites for Q called Q0 or QI. I guess it's probably QO. So we'll bind QO first, so 0. And there we are in QH2. What Q will do is it'll pump the 2 hydrogens it was carrying into the intermembrane space. It will give 1 electron to this iron sulfur protein unit. So again, we talked about that iron sulfur is there to move electrons. Then it will give an electron to cytochrome C. When cytochrome C has this electron, it can then leave. And it will go find complex 4. However, Q only gave off 1 electron. So we have this Q free radical. What a free radical is, it's an element that has an unpaired electron, very dangerous, very reactive. So we have to take care of this. And the way we're going to do it is actually kind of interesting. We're going to give that electron to heme. So this Bl and Bh, they're just different hemes. So we're going to give it to heme Bl. When we do that, Q is back to the original Q we saw in complex 1 and complex 2, no charge. And once you're in Q, once you're without the hydrogens, you can move to QI. So just to recap, if you're QH2, you can only move to QO. If you're Q, you can either be in QO or QI, but what will happen is that you're most likely going to be in QI. Once you lose that electron, you're going to go over to this QI. And these QO and QI, they're just places on the complex 3. They're physical locations in complex 3 where we're binding these Q. Right? So we pass an electron to heme Bl. This heme Bl will transfer an electron to heme BH, which will give the electron back to Q. So it's almost like Q did like a little bit of a handoff where it handed it off to heme BH, ran all the way to QI, and then accepted the proton back, right? I'm sure there's a football analogy there where you hand it off to the running back, you sprint down, the running back throws the ball to you. Anyways, I don't know what that called, flea flicker or something like that. I should not talk about football. Okay, once you got your electron back to free radical, you are trapped in QI, which is good because free radicals are super dangerous. And that's the end of phase 1. 1 Q molecule pumped 2 protons to the intermembrane space and gave 1 electron to cytochrome C. However, we still have this free radical Q stuck in complex 3, so we have to do something about it. So that's phase 2. A separate or different QH2 molecule binds than in phase 1. So these are actually 2 different molecules. And we go through these stages again, where QH2 loses 2 hydrogens, gives an electron to cytochrome. The cytochrome leaves to go to complex 4. You have a free radical Q. You give the electron to Bl and BH. Now, for the second cycle, when you give the electron away and you become Q again, QI is already occupied from cycle 1. So you can't go in there. That room is already busy. So you just disassociate. You leave complex 1, and you either go to complex 1 or you go to complex 2 to receive more electrons and hydrogens. But the electron that Q gave up goes to heme Bl, goes to heme BH, and it gives it to our free radical Q, which will also accept 2 hydrogens from the matrix of the mitochondria and form QH2. And once you're at QH2, you are free to leave. But, where's QH2 going to go? It only has one place to go. It goes to complex 3. So you can actually restart this process with the same Q and just keep doing this cycle over and over and over and over and over again. So it takes 2 Q molecules to actually do a full round of complex 3. And that's why it's called the Q cycle. And that is the cycle in a nutshell of how we are finally cashing in our Qs, giving the electrons to cytochrome C, pumping the hydrogens into the intermembrane space, and then moving on to complex 4. So are there any questions on how the Q cycle works? Did I lose anybody with that explanation, or anybody wants any clarifications or anything like that? Let me know. Would the big takeaways be the Qs or the electrons? So for the cell, what the cell cares about are the electrons. They want the electrons to move on to complex 4. And they also care about the protons being ejected out, because it's those protons that we're going to use to make ATP later on. And the energy for pumping out those hydrogens, those protons, are coming from this movement of Q, of the electrons from Q. Because every time we move electrons like this, it's always free. We're always giving electrons to molecules that want them more and more and more. So it's both. That's the big takeaway here. It's how are we moving the hydrogens and electrons from Q in a way that's productive for the cell? Yeah, how is that happening? So not really an answer to your question other than they're both the big takeaways, because it's important to know what happens to Q. And it's important to know how the electrons are moving in complex 3 to accomplish all that. So sorry I couldn't give a better answer, but it's both. Because the Q, we need to recycle to go back to complex 1 or 2 anyways. If you ran out of coenzyme Q, couldn't move electrons anymore. Then the other Q, we can just recycle immediately. So other questions about how the Q cycle works? Anything from here that wasn't clear, or anything at all? All right. That allows us to go to complex 4 then. So from complex 3, we made those cytochrome C. And that's floating around in the intermembrane space. And those will come and bind to complex 4. And for this to really work, you have 4 molecules of cytochrome C binding at once. And they will pass their 4 electrons to oxygen to make water. So finally, at complex 4, we have made it to oxygen to make our water. This is a huge complex, 410 kilodaltons. Each part of this complex, it's a homodimer. So dimer, again, means two. Homo means the same. So it's two of the same proteins coming together to make a big complex. Each of these dimers, 13 subunits. So just very big a protein. 3 of these subunits are extremely hydrophobic. And if you remember when we talked about the mitochondria, there are about 10 proteins that the mitochondria still makes on its own because they're so hydrophobic, they can't be transported through the cytoplasm. 3 of those 10 are from complex 4. 3 of these proteins are so hydrophobic, and it's like the cream colored proteins right here, that they have to be made in the mitochondria. So the way that we're really moving electrons around again is we're using hemes. Hemes are going to be our shuttling. And here you can see oxygen bound to an actual copper and a heme. And it's here that, like I said, for every 1 molecule of oxygen, we're going to transfer 4 electrons and 4 protons to make 2 units of water. And unlike complex 3, where we look at the Q cycle, I don't believe, we're not going to look at complex 4 in that great of depth. So just know the overall reaction here. Know that cytochrome C comes in from the inner membrane space. Know that you need 4 of them. Know that oxygen is the accepting molecule to make water. And that is pretty much it for our 4 complexes of how we move electrons all the way from NADH, or succinate, to oxygen. And every time we're doing that, except for complex 2, we are moving protons around, and we're going to cash in on those protons. So complex 1, 3, and 4, we have protons that are going against the gradient. And now when we talk about ATP synthase, we're going to allow them to go back with the gradient and diffusion and use that power to make ATP. So overall, that's the whole reaction right here. And I'll rewrite what it says in green. ADP plus PI goes to ATP, moving hydrogen through our ATPase, which we'll talk about in a little bit here. So just talking about the electron transport chain, this was really discovered through some key experiments that I have listed here. One, if you remove the inner mitochondrial membrane, you have destroyed oxidative phosphorylation. So scientists have learned, to do this, you need an inner mitochondrial membrane. And when they look at the inner mitochondrial membrane, they notice that it's impermeable to small ions, protons, hydroxides, potassiums, chlorines. So that's another piece of information. The inner mitochondrial membrane does not allow small ions to go through it. And when you look at electron transport, you're taking hydrogens, you're moving them from the matrix to the inner membrane space, and that actually creates a current that's measurable. So what happens when you allow the electron transport chain to run? You can measure the electrical current, showing you that protons are moving. And then if you allow the inner mitochondrial membrane to become permeable to small ions again, so you just add some chemicals and you don't destroy the membrane, but you allow small ions to go through the membrane, ATP synthesis is destroyed. So taking all of this into consideration is how people really have deduced how this very complex system works. I mean, when talking about we can break it down in simple terms, but trying to actually study this in the mitochondria was a giant effort. And some of those key observations are really what helped to explain how this process works. And you can actually uncouple the ATP making part of oxidative phosphorylation, where you can just allow protons to pass through another port rather than ATPase. And this actually happens in brown fat. So in brown fat, you actually have another channel that's not ATPase, which allows protons to go through. And when you do that, all you are doing is you're generating, generating heat. So that is how, like, babies, they have a lot of brown fat because they have tissues that will do oxidative phosphorylation to pump hydrogens out, but they're not using that proton gradient to make ATP. They're using that proton gradient to generate heat from themselves. So you can have oxidative phosphorylation without ATP synthesis. But we're going to be mainly interested in ATP synthesis. So that is what we are going to discuss next, this ATPase molecule. But up to this point, let me take a pause here and just ask questions about anything anyone might have so far. All right. So to really make this free energy, we have to have that proton gradient, which again, complex 1, 3, and 4, they're using the power of moving electrons. They're using that free energy to pump hydrogens from low to high. So they're going against diffusion. And this free energy, which is called proton motive force, proton moving force, or PMF, that is what is going to power ATP synthesis for us. And the energy of this, we can calculate this. Delta G of transporting a proton is 2.3 times R, gas constant, times T, temperature, multiplied by what is the pH of the matrix minus the pH of the intermembrane space. So if you remember, like what I just said, we're pumping from the matrix to the intermembrane space. So the matrix will be a high number, and the intermembrane space will be a low number. Because remember, the more hydrogens you have, the lower the pH you have. Plus Z. Z is the charge of a proton, so it's really +1. That's always 1. F, Faraday's constant, 96,485, multiplied by the membrane potential. That is, what is the charge differential between the intermembrane space and the matrix? So again, let me draw this out. Intermembrane space, matrix. This has a lot of positive charges. Therefore, the matrix will not be as positive charged. So we say that the membrane potential is 0.186. So for moving protons from the intermembrane space to the matrix, that's a change of negative 0.168. That's how it works. If you're moving from positive to negative, this membrane potential is you just represent it as a negative number because you're going from positive to negative. If, on the other hand, you're going from the matrix to the intermembrane space, that is positive 0.168. So that's kind of how you keep it straight in your mind. Am I going from positive to negative? Then my membrane potential change is a negative number. Am I going from negative to positive? Then it's a positive membrane change. When looking at the pH differences, it's roughly 0.75. So delta G for moving one proton is 21.5 kilojoules per mole under these conditions. To make ATP, you need roughly 40 to 50 kilojoules per mole. Therefore, as we'll see, just talking about energy, you need roughly 3 protons for every 1 molecule of ATP. So that's the mathematics of what's happening here. And of course, I would not give you a math equation and expect you not to know how to use it. So we're going to do a little practice. Get you right in there. So here's my equation again. R is, oh, I have it right there, 8.314. Faraday is 96,485. I think it's joules, volts, moles, if I remember right. Right, so here's a calculation for you to try. The difference in pH between the matrix and IMS, is 1.4 pH units. If membrane potential is 0.06, what's free energy for transporting 1 mole protons across the membrane from outside to inside? So from intermembrane space to matrix at 25 C or 298 K. And once you do that, tell me how many protons I need to make ATP if we just say you need 30.5 kilojoules per mole. So I'm going to give everybody a couple minutes to do this while I go and see what my dog is losing her mind about. If you have questions, let me know. I'll put it in chat. Otherwise, I will be back in a few minutes to help you work this out. But try and take a stab if you can figure out this equation. Let me put up a poll real quick, just so I can get a sense where people are at. And I'll go over this in about 30 seconds. 30 seconds to like a minute. Just gotta get my math pulled up here. All right. So seems like nobody's confident, but at least we were able to get part of the way here. So let's draw a picture. Matrix. I guess I can make my picture way better. I don't know why I'm doing it tiny. Matrix, inner membrane space. All right. So the difference in pH between the inner membrane space and the matrix, this delta between these two is 1.4 pH. Right? So what has what has more protons? That would be the IMS. So if you wanted to put like fake numbers, you can do that. So let's say, and this is complete BS, but let's just say the matrix has a pH of 6. And let's say the inner membrane space has a pH of like 4.6. The difference between these two is 1.4. So we can plug that in. So delta G equals 2.3 times R. R is 8.314 times T, which is 298. All right. Times the pH of the matrix. Like I said, I just made that up, which is 6, minus the inner membrane space, which is 4.6, or the difference is 1.4. Plus Z. Z is the charge of a proton. So Z is 1. Times Faraday's constant, 96,485. Multiplied by the membrane potential. Okay, so the membrane potential is 0.06. Again, we said that outside is positive, inside's negative. So I'm moving from positive to negative. So the overall charge is negative 0.6. Or sorry, 0.06. Negative 0.06. So there's two parts of this. This is the first part before the plus sign. This is the energy due to diffusion. The second part is energy due to charge. So, and I write that down because when doing this and talking through it, I did notice an error. All right. So what is the error that I noticed? Okay. So the way I have this pH of the matrix minus the pH of the intermembrane space, this is written for moving protons from the matrix to the inner membrane space. So that form of the equation is correct going this way. However, and I apologize for this, I just noticed that right now, if you are going from the inner membrane space to the matrix, these two pHs are flipped. It's actually the pH of the inner membrane space minus the pH of the matrix. And so my numbers should be reversed. It should be 4.6 minus 6, or a negative 1.4. So this is actually a good teaching moment. How did I know that my equation was flipped? I didn't memorize these equations or anything. The reason I knew that is because delta G, remember, if it's negative, that's spontaneous. That's favorable, right? And so this first part is the energy due to diffusion. And we're going from high concentration in the inner membrane space to low concentration in the matrix. So that's a favorable reaction. You should get a negative value for the first part of the equation. However, when I originally wrote it, I saw that we were going to get a positive value. So that means that I wrote this backwards. So always be plugged in as best as you can when doing math. Keep asking yourself, is the result I'm getting, does that make sense? Based on what I know of biochemistry, if I'm moving protons from high concentration to low concentration, that should be favorable. So my energy should be negative. Right? So I apologize for giving you the equation that was slightly backwards, but we do this math and you should get negative, if I did all the calculations right, negative 7,977.78 joules per mole. If you got something different, let me know, because I'm going to trust that I did my calculations right. Plus, and the second part is actually minus because the answer is a negative. Negative 5,089.1 joules per mole. And combine these two together is negative 13,766.9 joules per mole. We can convert that to kilojoules per mole by dividing this answer by 1,000 to get negative 13.7, I'm just going to round to 77 kilojoules per mole. Then to find out how many protons I need to move, you just take 30.5 divided by 13.77, and you'll get, you need roughly 3. It won't be a whole number, but you always round up. Like it's going to be 2 point something, but you can't like have a quarter of a proton, so you just round up to 3. So using these conditions, you need 3 protons to move to make 1 ATP. All right, now that you saw this worked out and the logic, try to explain it, is there any questions on this equation, anything I did, anything at all? How did I get 3 again? So to get 3, I took 30.5, which is the energy for making 1 ATP, divided by 13.77, which is the energy of 1 proton coming across. And doing that, that's 2.2, but you always round up because I can't have 2/10 of a proton. So I need at least 3, right? if I only have 2 protons going through, that's not enough energy for 30.5 kilojoules. So I need 3 protons to get my required energy to make 1 ATP. Any other questions about the math for moving protons across the membrane? And of course, if I ask you the opposite question, what's the energy? If this was moving hydrogen from the matrix to the intermembrane space, the only thing that would change are the signs. This negative 1.4 would be positive 1.4. This negative 0.06 would be positive 0.06, right? So the thing to keep in mind with this, if you're moving into the matrix, your energy should be negative because they're spontaneous. If you're moving to the intermembrane space, your energy should be positive because they're non-spontaneous. And the reason we can do that is because we are transferring electrons from like NADH to UBQ, or UBQ to cytochrome C, or cytochrome C to water. That's where we're getting the energy to do that non-spontaneous reaction. All right. Now that we looked at the math, now that we looked at the 4 complexes, let's move on to ATPase, ATP synthase. And again, what we're looking at here is we're looking at a bacterial version. Again, that's why you see the periplasm in the cytoplasm here. But it's the same thing in humans, same thing in eukaryotes, same kind of structure. This thing is massive. Many different proteins coming together, 450 kilodaltons. Again, that's very, very, very heavy. There's basically 2 parts to this, F0 and F1. F0 is in the membrane, so that's why it says water insoluble. And let me just point these out. So these hot dog looking big old barrels, that's unknown structure. For this A part, it's so hydrophobic that it's really hard to get a structure out of. As for this connectors, I'm guessing these connectors are too flexible to really know what the structure of. So we know the structure of most of this complex, except these barrel looking parts. So F0, that's in the membrane. F1, that is the soluble part that's going to be poking into the cytoplasm for our prokaryotes. So you got a water soluble and water insoluble part. And ATP synthase basically has 3 different conformations it can be in. So each part of ATP, each molecule of ATP synthase has 3 different areas where chemistry can happen. And each of these areas have 3 different states, conformational states they can be in. It can be in the L, the T, or the O state. So let's take a look at this on the bottom left. So each one of these areas that are these half circles, they are made out of 2 different parts. They are made out of an A part and a B part. And for our 3 conformational states, L, T, and O. L means you bind loose. T means you bind tight. O means you do not bind. Only one subunit can be in a state at a time. So you have one O subunit, one L subunit, one T subunit. This green thing, that's like the motor. it represents this middle alpha helix here. This is what's going to be physically moving during this operation. And that is what is changing the conformational states. In transitioning, the way that we transition is that if you're an O, you always go to L. If you're an L, you will always become T. And if you're T, you'll always become O. So that's how we're moving. We're going OLT back to O, OLT back to O. So let's take a look at this. In the T state, you are binding substrates and products tightly. So here, when we start, we have ATP. And our first step is we're going to bind ADP and a phosphate. Because remember, the whole point of this is to make ADP. And this binds in the loose. So here we bind loosely. O doesn't have anything bound to it. Now, what happens is that 3 protons will move through ATP synthase, generating energy for us, and causes our more or less piston to turn, or our crank, I guess. It's not really a piston. This will cause the T state, the tight state, to become open. When you're open, you don't want to bind anything. So ATP leaves. The loose state is going to become tight. And so what's happening is that in the loose state, the way to kind of imagine this, our ADP and phosphate are kind of like far away. So it's like if you have your hands and they have ADP and phosphate, they're kind of far away from each other. Then in the tight state, you more or less bring these together so that they're really close. So if you're doing the hands example, they're far away from each other. You bring your fists closer together, and you smash them together, and you make ATP. So that's why ATP leaves the O state. You now have ATP in your new tight state. You also lose water at this point. And then the process can start over. New ADP and phosphate binds in your new L. Energy will cause a transformational change. And so this will become L, ready to accept a new ADP and phosphate. This will become T, where ATP will be formed. And this will become open, so ATP can leave. And it just repeats over again. And that is basically how you are making ATP using ATP synthase. So any questions about our different states or what is happening biochemically with ATP synthase? All right. So how do we generate the energy needed to make these conformational changes? And the way I really think about this is that ATP synthase is like a giant merry-go-round, right? So again, we're looking at the bacteria form. That's why it's periplasm and cytoplasm. This should be intermembrane space and matrix. So when we look at this complex, the ring, the F0, the F0 unit is made out of what are called C ring. So they're just a bunch of proteins that form a giant ring. And on these rings, you have space for protons to bind. So a proton will go through this A subunit, which again, we don't know what it looks like. So that's why it's just like a giant circle. Protons go in and bind to a location on the C ring. Then these protons will go a full turn until they get nearly back where they started. And then they'll be pumped out the other side into the matrix. And again, this is high proton concentration. This is low proton concentration. So the protons do want to go over to the matrix, but they have to go on this merry-go-round first to get there. And so it's actually super clever. That is what is propelling this change. This turbine spins, causes, and this turbine, this F0, they're combined, they're connected to F1 through this gamma subunit. And you are causing this conformational change to happen in your A and B subunits that we just talked about, making ATP formation. So that is basically what's happening. And for every one turn, you get 3 ATP. This really isn't all that different from how we generate electricity. You have a magnet going around in a circle, and that causes electricity to be made. For us, we use gasoline to do that. In the body, you're using protons. So any questions about the basics of how ATP synthase actually moves due to proton motive force? Well, so a question might be, why does binding a proton cause a protein to move? Well, let's take a look inside these C subunits. And the C subunit is really just 2 different helixes. And they're just different lengths. And connecting these helixes are 4 residue little loop right here. What happened to my pen? Oh, holding it upside down. So 4 residue loop connecting these 2 different helices. What happens is that when a proton comes in, we think it binds to aspartic acid 61. Hopefully you remember your side chains. Aspartic acid is negatively charged. That makes this aspartic acid neutral. When that happens, this helix straightens out. This straightening out of the helix pushes against the other helix and causes an actual mechanical change in the whole subunit that causes it to rotate. And it is this whole straightening out the helix and then losing the proton to bend the helix that is causing the whole C subunit, the F0 subunit, to go around in that merry-go-round fashion, causing ATP to be created. So that's actually what's happening on the molecular level to cause this movement. The question is, how do we know this actually happens? This was a very cool experiment that was done. So what some researchers did is that they took actin and they had a fluorescent label on it so that it actually glows when you look at it in a microscope. And they just connected it to the C ring. And they allowed protons to flow through this ATP synthase. And here's the result. What you can see is that this actin filament is moving. So that white part is the actin. And over time, it is rotating 360 degrees. I know the last part's kind of cut off for you, but that's what they're seeing. And so this is actually showing on a visual level that yes, ATP synthase is working the way we think it does, that it is a rotation in the C subunit caused by protons. And it's this energy that is being connected to these alpha beta subunits in F1 to cause the creation of ATP. So that's just a cool experiment to show, this is actually how it works. And I think I have one more question for everybody, then I'll let people go. We're actually on time for the first time ever. So based on what we just talked about, I will tell you that according to the Cryonics Institute Technology for Life, that they will freeze someone who just recently passed away and keep them in liquid nitrogen for the low cost of $35,000 a year until medical science has advanced to cure them of whatever killed them. Based on everything you have learned in biochemistry, and specifically from what we talked about today, why is this like most likely impossible? What is the flaw in this idea? Does anyone have any ideas why you probably should not freeze your deceased loved ones for $35K a year? Well, rich people and their money. Any thoughts, ideas? Doesn't have to do with unfreezing them. Yeah, that could be a big problem. Why do you think that might be a big problem? Price? Well, let's say that you're Jeff Bezos, so you don't care about price. Price and you're already dead. And wouldn't it disrupt the chain of energy flow? Yes. Wouldn't it just stop every mechanism in your body? Yes. The idea, so you're all correct. The idea that they say is that when you freeze, you're in like, I don't know, Star Trek. Do they have this? I don't know. I've never seen Star Trek, where you're in like a suspended animation where like you're kind of just like not doing any biological part. Yeah, stasis. So one, let's talk about freezing. When you freeze somebody, the water in their body also freezes. And when water freezes around proteins, it destroys proteins, it destroys membranes. And so when you unfreeze them, their proteins are destroyed. So good luck trying to get them to live after that. But just relating it to what we talked about today, the whole reason we are basically organic power plants is because we have a membrane that is allowing us to have a difference in proton gradients. And when you die, what happens is that entropy starts to take over. I believe someone said that. And your membranes will start to break down. And so your proton gradient will start to balance out, especially because you're not breathing oxygen anymore. So your proton gradient, there's nothing there's no electrons that are being used to push against the gradient anymore. So you're not pumping protons out. So naturally, your protons will flow through ATP synthase until you're at a gradient, and now you can no longer make ATP. So let's say I was dead for like 2 hours. My proton gradients are gone. And then you freeze me and unfreeze me like 200 years later, my gradient's still gone. I can't like make ATP well anymore. So just biochemically speaking, what we know about proteins, what we know about gradients, not likely to happen. There are other organisms that can do torpor, right? Granted, yeah, so it's mainly because this is one, they're human, so we're very complex, and it's very cool. Someone just rang on my doorbell, so I have to go. It's end of the class anyways, so I will put up a homework. I need to go calm my dogs. If you have any questions, let me know. Otherwise, I will see people on Thursday. But yes, sorry to leave so abruptly. If you want to talk about cryo electrons more, just let me know. Otherwise, I'll see people later.